now we just simply take this triangle and give it labels and declare it Eithoven's triangle. So it's always the subject's right and left. So this is the right arm, this is the left arm, this is the left leg. Now, what about the right leg? I don't want you to do this on here. You can do it on your little worksheet that has a little mock-up triangle on there. You can mark it on there if you wish, but don't mark it here. The right side is marked this way. This is the ground. That's the symbol for grounding. And we call it RL. Okay? But like I said, don't do it here. Do it on your worksheet. All right. The next thing we're going to do is we're going to establish our isoelectric points, which are simply the center point, 0, 0, and 0. We're going to now show where the eye of the machine is. Where is the machine looking from? From here, it's looking at the heart, it's down on the heart from lead 1. From here, it's looking from the right, and from here, it's looking from the left in lead 3. So lead 1 from the top, lead 2 from the right, lead 3 from the left. And these are called bipolar leads because if it's positive, it's recorded in an upstroke. If it's negative, it's recorded in a downstroke. How do we know what side is positive, what side is negative? Well, just remember that the right arm, no matter what, is always negative. The left leg, no matter what, is always positive. Okay? So if I make the right arm always negative and the left leg always positive, it only leaves the left arm, which has to be positive in lead 1 and negative in lead 3. Okay. So go ahead and do that. And now our Eithoven triangle is complete. So go ahead and title it Eithoven's triangle. Okay. Wilhelm Eithoven is the electrophysiologist that invented / discovered EKG. Okay. Now, yeah.
The right leg, is it part of the triangle?
No, like I said, don't put this over here. Put it on your mock-up worksheet. This is how we represent where the right leg lead went, the lead electrode, the skin electrode. We don't use it. We don't use it for Eithovens. It's not part of the triangle. But it is used to be a ground. Okay? Safety. So if you got shocked or if there was a lightning strike, you'd be protected. Okay, so now let's put those numbers down. I'm going to mock up some numbers here. 5, 9, and 4. Okay? Those are the 3 numbers I got. Now, anybody have any huge numbers, like 20, 15, 10, anything like that? Any numbers past like 8? Huh? For your height of the R wave. If you got huge numbers, there's a couple of things you can do. One is just good old-fashioned scaling, because you're going to be basically drawing a triaxial graph. So if you only had 10 squares and your largest number was 30, what would you do? You'd make each square count for 3, right? Isn't that what you do when you scale? Okay. All right, that's one way. The other way is you simply take your smallest number and divide it into all 3 numbers. So let's say it was 5, 14, 5, 15, and 10. 5 divided by 5 is a 1. 5 divided into 15 is a 3. 5 divided into 10 is a 2. So your numbers would be 1, 3, and 2. Okay? It's however you want to do it. Okay? Or you can just simply do a scale and just figure out a scale. So in this case, my largest number is a 9. Okay? I can simply go all the way across to 9 if I want to, but do I really want to? Because now I'm kind of approaching the end of the triangle. So what I'm going to do is I'm going to call each square 2. So 5 would be 2.5 squares. 9 would be 4.5 squares, and 4 would be simply 2 squares. Okay? So you figure out what scale you want to use. Now the question is, how do I put these numbers on the graph? Well, here's what I do. For number 5, I'm going to go ahead and simply mark 2.5 and then draw my line. Now, this is where your reticulated ruler comes in very handy. You notice that you got little graph marks on there. I line up the top line with one of these established graph lines, and I will, with confidence, draw a straight line. Okay? Like so. That's a perpendicular line to the top line. Now, how do I draw 9 over here? Okay, I got that same problem again. How do I mark off 9 squares? I'm sorry, 4.5 squares over here. Well, once again, I'll use my compass to help me. I'll mark off 4.5 squares. So there's 4.5 squares, which represents number 9, right? But what I'll do is, I'll bring this measurement over here. And since it is a positive 9, I'm going to mark it in the positive direction. And my next number is 4 for lead 3. So I'm going to measure out my 4, which is basically 2 squares. And I'm going to put it in the positive direction, like so. Right here. Okay? So go ahead and do that. So once you've marked off all 3, all I'm going to do now is I'm going to draw perpendiculars for each of the lines from that point. So I'm going to mark off a perpendicular here. You understand perpendicular, right? 90 degrees?
Yeah.
I'm going to mark off a perpendicular here. Okay? And what I create is should be ideally a point, but it may not always be a point between these 3 lines. I should create a point. This is the apex of the heart. The center of the triangle is the AV node of the heart. So electrically speaking, your heart is sitting like this, somewhere in here. Okay?
What does that mean? Electrically speaking.
Well, because you're doing it all by electric numbers. That's all you have. You just have, these are all measurements of voltage. Okay? Now, let me finish the idea and maybe you'll get it in a little bit. What I'm going to do is I'm going to draw a line now that will represent the direction in which depolarization happens. So just watch here for a second. Okay? I'm going to draw a line from the center of the triangle through the apex, and that's the direction in which the heart is being depolarized. Okay? Now, there's a reason why I'm going to draw it all the way to the back, and I'll explain it to you in a second. But this is called the ventricular axis. The heart is pointing in this direction, electrically speaking, meaning the only thing we have to look at is what the EKG is recording. Okay? So the heart is pointed in this direction electrically, and it's a combination, it's a tug of war between the left heart and the right heart. The left heart pulls the axis one way, the right heart pulls the axis another way. And this is what you come up with. Okay? In most people, the axis is going to be pointed to the left. Okay? What's that? So what have we done so far? We've taken the first line off of the first number, dropped the perpendicular. We took the second line number and dropped the perpendicular. We took the third line number and dropped the perpendicular. And where they cut, we got ourselves an axis. Now, if it doesn't cut, if it makes a tiny triangle, then just take any one of the points of the triangle. Or for that matter, take any point in the triangle. Okay? That's your little margin of error, basically. And that'll be your apex. And this will be the beginning of your ventricle depolarization. This will be your AV now. Okay? Now, the last thing we got to do is come up with what we call the ventricular axis deviation angle. Now, why do we need to know this? Well, if the heart is pointed to the left, electrically speaking, okay, the heart is pointed to the left, it's because you've got a lot of left ventricle pulling this way. If the heart is pointed to the right, then the heart is being pulled this way by the right ventricle, electrically speaking. So that implies that you either have left ventricle bulk or right ventricle bulk. To a certain extent, it's the left ventricle that should be bulkier than the right, correct? Because left ventricle is sending blood, high pressure, etc. So it should be, the normal range is anywhere from -30, which means beyond 0, -30, all the way to +105. It would still be considered normal. But if you go beyond -30, or if you go beyond 105, then one or the other side is getting too thick. If it goes beyond -30, the thought is that the left ventricle is getting too thick. And if you go beyond 105, maybe the right ventricle is getting too thick. Now the question is, why would the ventricles get abnormally thicker? Well, one reason is the ANREP effect. Remember? Where there's too much back pressure, the ventricle is getting a lot of resistance. Okay, so why would it happen on the right side? The right side should be low pressure. Maybe there's blockage in the pulmonary system. Maybe the lungs are too scarred. Why would it be happening on the left side? Maybe it's obesity. Maybe it's atherosclerosis. Maybe it's some other problem that, hypertension. Okay, that's making that left ventricle work harder. Okay? So the important thing is that whatever that number is, it should be within -30 to +105. So what I would have to do, and let me just show this to you first, okay? Since we got it on, are we still recording it?
I was recording earlier.
Oh, okay. Well, do you have a way to record this, or somebody have a way to record
I'm
this?
recording it.
Okay, you're recording it? Cool. Okay, so what you would do, and don't do this to yourself right now, okay? I'm just going to show this to you. What you would do is draw a line that's parallel to this line, the top line, and basically now you've established 0 and 180. And you simply measure this angle. Okay? But now, maybe that's